Hey everybody, welcome back to Organic Chemistry. My name is Todd Rothman. In this video, we're going to go over how to distinguish between different H's in a molecule. So at this point, we've already gone through all the theory about NMR. We understand the basic characteristics, right? And that is that when you have this applied magnetic field that is surrounding a molecule, that the molecule, its protons, will have these defenses. If we're dealing with HNMR, they'll have these local magnetic fields that defend themselves against the applied magnetic field. Now, the key to this is that not all local magnetic fields are the same, and it all has to do with the electron distribution or density, right? So not all H's are going to have the same amount of electron density around it. And the ones that do have more electron density are going to defend itself more against the applied magnetic field. So all this should make sense. If none of this makes sense, you have to go back and watch that first video, okay? Because I went over all the philosophy. All right, so this video is about how to identify the different types of protons in a system, in one molecule. The next video that follows will talk about where they would be on a chart. So, you know, which one would be further up or downfield in a chart. All right, but I'm assuming at this point that you've watched that first video. It was about an hour long, and it gives you all the fundamentals that you need to know to continue. Okay, so if you didn't watch it, make sure to do it now. Otherwise, let's get started. So the first thing I want to talk about is equivalent versus non-equivalent hydrogens. Now, from this point forward, let me make this clear. It says it right here that we're dealing with HNMR. Very important. So this entire series is almost exclusively focused on HNMR. Once you get HNMR, it's easy to learn the other types of NMRs. We're going to focus on H, and we'll do a little introduction to CNMR at the end. But primarily, our focus is on HNMR. Okay, so now instead of more generically, we're going to focus in specifically on this characteristic. So the first thing I want to talk about is what does it mean to be equivalent versus non-equivalent? Well, remember that when you have a molecule, it can have many H's, but they're not necessarily different from each other. Some will be the same type, or they'll have similar property for this particular experiment, whereas others might be very different. And so we have to be able to figure out how many H's are the same and how many H's are different in order to figure out how many readings ultimately we'll get on a chart. Okay, so that's what we're going to do now, is to figure out how to do that. So let's start with the very basic methane. So if we have a carbon and this carbon has 4 H's around it, the idea here is that these H's are connected to the exact same carbon, right? So they should have the same exact electron environment. There's some electron distribution around them, and it's roughly about the same, right? It's equally distributed. So this molecule, although it has 4 H's, is only going to give one reading, or one chemical shift to represent all of these H's. Now let's think about why before we get more complicated. An H's electronic environment is its defense, right? Remember that? So the closer it is to the nucleus of the proton, of the hydrogen, then the more it could defend itself against the big magnet. Now, what makes H's different is when the electron distribution is different around them. But if you have H's and they're all touching the same carbon, then they're all going to have the same exact electron distribution. Now, we'll see differences in a moment, but that's the general idea. Think about it. This methane has 4 H's, and they all have just about the same distribution, roughly the same, of electron distribution. So they have the same local defense. So when you turn that dial and you get that radio frequency to a certain amount, when you hit that amount, they're all going to resonate. They're all going to spin flip at the same time. So you get one reading. You don't get more than one for these H's. Okay? Now, let's take it up a notch to ethane. Now, in the case of ethane, we have 2 different carbons holding 3 H's, right? So if you look at the structure, you might say that these H's are different. Now, the ones that are on the same carbon, I think we could appreciate are the same. They have the same electron density distribution, right? However, what about the other carbon? Well, here's the thing. When you look at a carbon that's single bonded, right? This is a sigma bond. The most important thing about a single bond between 2 carbons is that it has full rotation. So the H on top is going to experience the exact same environment because of rotation than all the other H's. So these three H's are all going to have a chance to be in that same exact environment because of rotation. Now remember, at room temperature, we're constantly rotating. So it's constantly going through this process. So all these H's have the exact same environment around them. Now, because there's a symmetry, because it's just methyl twice connected together, that means that the same exact environment on the left is what you would expect on the right. So these H's over here, although they're not on the same carbon, they have the same carbon type, right? There's a symmetry between them. So what we can assume here, and we'd be right, is that these H's all experience the exact same electronic environment. They have the same local defense. So they're going to all resonate at the exact same time. So let's write that down. There's one chemical shift for all H's, for all 6 H's. So you're going to have one reading on a chart. If I had a chart, then they both are going to have just one reading. Now, we don't know more about this reading, so we're not going to get into the details yet. But what I'm saying is that because they have the same electronic environment, they're going to have the same reading. They're going to ring flip. They're going to spin flip at the exact same time. Okay, they're going to resonate at the same time. Okay, so now the next thing I want to talk about is, let's say we add a carbon to this. So let's go to propane. So when we look at propane, we have 1 carbon, 2 carbon, 3 carbon. And now we have our actual difference. Now, again, these are all sigma bonds that are connecting them, right? This is a sigma between the 2 carbons and sigma. So because it's sigma, we know there's full rotation. And for that reason, the H's on this carbon are all the same. They all will experience the same environment when they spin around. They all get a chance to be up or down or back or forward, or, you know, they all have the same positioning. Okay. Now, the carbon on the ends are the same because they're both connected to this central carbon and they're both methyls. So since this is a methyl and this one's a methyl and they're both connected to the exact same carbon, that means that they will give one reading because they have the exact same environment. They're going to spin around in space and they have the exact same electron distribution. So the methyls are going to give us one chemical shift. But now let's look at this middle one. This one in the middle, this H and that H, they're on a carbon that is different than the ends, right? The ends have a carbon with 3 H's on them. Whereas these 2 H's are on a carbon that does not have a methyl. It's not a methyl. It's called a methylene. It's a carbon that has just 2 H's and 2 single bonds. So it is not the same as the outer carbons, right? Or the outer H's, right? So a lot of times I look at the carbon when I'm thinking about the H because really it's about who it's connected to. The H has to be connected to someone, and if you think about what that someone is, that something is, you'll figure out the environment that those H's are in. So the 3 H's on the ends, this end here and this end there, they're the same because they're all methyl and they're touching the same carbon. But the carbon in the middle is different. Those H's on that carbon are not attached to a methyl, they're attached to something else, which means that they're unique. They're not the same as the methyl. So we would say that the green H's, although they are the same, right, because they rotate in space, so they have the equal distribution in space, they'll always have the equal chance of being in the same place, right, at different times, and they have the same electronic environment. They're connected to the same carbon. So they're the same, but they're different than the ends. So these two are going to give one chemical, these 2 H's will give one chemical shift. So in total, we will have 2 shifts in our chart. We're going to have 2 readings in our chart. So when you turn that radio frequency, you're going to hit the first one, and then a little bit higher up, you'll hit the next one. Okay? And so you're going to have 2 different readings. Now, this is an easier way to do it. So the key here is to look for plane of symmetry. So if I have a propane, it's easy to do it without drawing the H's out. So right here in the middle is a plane of symmetry. That carbon